Okay, we're continuing with more counting example problems. This is part 6. And so once we got into really part 3 and part 4, the level of difficulty was really high. So at this point, we're not getting any more difficult. We're just working a bunch of different counting problems. Okay, 8 women and 5 men are elected for president. How many ways to choose a winner? So this is just, there's 13 potential candidates, and it's kind of a trick question because there's 13 ways. That's it. There's 13 potential outcomes. Okay, how many man versus woman pairs can we make? Man versus woman pairs. So here we've got 2 events that they're separate events because one we're pulling from a group of 8 men, and the other we're pulling from a separate group of, it's 5 men, and then here we're pulling from a separate group of 5 women. So there's 5 potential outcomes here, and there's 8 potential outcomes here. So we want to multiply these. And remember, you might be thinking, well, don't we have to apply the division rule because we don't want to count reorderings? There is no reorderings here. These outcomes are based on a certain group. These outcomes are based on a separate group. You can't have a certain woman come over here. So it's just 40. How many ways can we choose a president and a female vice president? So, okay, the difference here is that for the first slot, we're not just picking from the group of men, right? We're picking from everyone. So these events are kind of tied together. So we have to be careful here. This is would be classified as more of a, falling in line with the permutation combination type problem, because this group that we're pulling from is dynamically related to the first group. So here we've got 13 potential outcomes, right? But now this group here dynamically depends on the first group, because if this was a woman, then we've got 7 items to choose from here. If this was a man, we've got 8 items to choose from. So we can apply the OR criteria here. So in this case, we would say there's 2 cases. If female president, then we've got, so in that case, it's just we're choosing from the 8 group of women for the president, and then there's 7 women left for vice president. But we want to do reorderings, because if Sally was elected president and Victoria was elected vice president, well, then we want to count if Victoria was elected president and Sally vice president, right? So, okay, so 56 in this case. Now, there's the other case where, what if we have a male president? Then, okay, there's 5 outcomes here, and then we want a female vice president, so there's 8 outcomes here, so 40. So 56 plus 40, 96. How many positive integers not exceeding 500 are not even or divisible by 3? Okay, so what this means is that we could rewrite this and say how many positive integers not exceeding 500 are not divisible by 2 or 3, right? That's what even means. You're divisible by 2. So we worked a problem like this earlier. So we have an idea of how to do this. We need to use like the whole Venn diagram idea. So, okay, but this is a little bit different because we've got this not here. So we have to keep that in mind. So all we need to do, because with the not, is just, so how many integers are there, positive integers are there that don't exceed 500? Well, there's 500, right? 1, 2, 3, 4. So we want to subtract. For the previous problem, we just found the different integers that were divisible by the given numbers, either of the given numbers. Here we're going to find that, but then subtract it from 500. So we want to start by figuring out how many positive integers not exceeding 500 are divisible by 2 or 3. That's what we did earlier. So, okay, in that case, we want to do so for divisible by 2, we divide this by 2 and do the floor function. So 250, not exceeding 500, so this includes 500. So there's 250 numbers, 250 integers between 1 and 500 that are divisible by 2. Now divisible by 3, we want to do, okay, so 166. Okay, so we've got our system of, so this is all of the integers between 1 and 500, but we want to subtract out the integers that are divisible by 2 and the integers that are divisible by 3. But there might be overlap. We can assume there is overlap, even if there's not. We'll just assume there is. So divisible by 2, divisible by 3. So we want to do, we're looking for, if this is A and B, we're looking for A union B, the number of elements in A union B. So what is the number of, so what's the number of elements in, we know this is the result. So, and then, right? So what's the number of elements in A? All the numbers that divisible by 2. It's 250. Okay, then plus in B it's 166. Now we just need to get it to figure out, are there any integers between 1 and 500 that are divisible by both 2 and 3 that we counted twice here? Well, okay, we can use the fact that these two numbers, 2 and 3, are relatively prime in that, so we can just take 2 times 3 is 6, and this will give us the number of integers that are divisible by both 2 and 3 from 1 to 500. So 83. And that's the intersection. So 250 plus 166 minus 83 is 333. But that's not the answer in this case, because now we're trying to solve, that's A union B. We're trying to solve for this. So we want to do 500 minus 333. $167. Determine the number of 6-digit integers, no leading zeros, in which, so digits may be repeated. So, okay. 1, 2, 3, 4, 5, 6. We've got this first option has, there's 9 outcomes, just can't be a 0. And that's the leading number. So now we come here and we're thinking about, this is just going to be permutation with repetition, where you're choosing from 10 items. So it's just 9 times 10 to the 5th. Okay, now no digit may be repeated. So in that case, we've got 1, 2, 3, 4, 5, 6. There's different scenarios here we need to analyze. Okay, if we can't pick a 0 here, so we can, let's say there's 9 outcomes. Okay, now we could pick a 0 here, but then we can't pick whatever this number is, so this is 9 outcomes as well, right? This can't be a 0. So this is some integer from 1 to 9. But this can include, it can include that integer, but it can include 0, so it's also 9. Then we've got 8, 7, 6, 5. So, yeah. So we didn't actually need to apply an OR criteria between different scenarios there, but here I think we do. No digit may be repeated, but an even number. So, okay, in that case, we've got so we need to analyze the cases where the last digit is 0, 2, 4, 6, and 8. Okay. So no. Oh, no, you can do this. Okay. So the first digit is going to have 9 possible outcomes because it can't be 0. Right? Then we've got 1, 2, 3, 4. The last digit is fixed. We're not multiplying anything. Like there's no outcomes to multiply here. It's 1. The outcome, it's 1. Yeah. Okay. Now, these can't be, let's see, this first one here. We've got 2 digits taken up. We know this isn't going to be a 0, and we know this is a 0. So it would be, 8. There's 8 options left. Then 7, then 6, then 5. Okay. Now, if the last digit is a 2. So there's one option here, but now this is going to be an 8 because this isn't 0, but then the first digit can't be 0. Right? This digit can't be 0 and it can't be 2. So there's only 8 options left. Now we've got, let's see. Now there's 8 options left. Is that right? Yeah, because this could be a 0. And we have 2 digits taken up. So 8, 7, 6, 5. Okay. Now, the 4, 6, and the 8 are just going to be a repeat of this. So what we've got is 9 times 8 times 7 times 6 times 5. And then for this, we've got 4 times 8 squared times 7 times 6 times 5. So it's just 8 squared times 7 times 6 times 5 times 4. So the answer, the final answer is 9 times 8 times 7 times 6 times 5 plus 8 squared times 7 times 6 times 5 times 4. Okay, now digits may be repeated, and it's an even number. So, okay, same idea. Last digit is a 0, 2, 4, 6, 8. So if the last digit is a 0, then there's one option here. You are allowed to repeat digits, but this can't be a 0. Okay. Now, we're left with, let's see. This is just 10. You can repeat digits, right? But the last digit has to be a 0. So there's just one option here. This, it's going to be, it should be the same, right? You have a 2 here. This could be a 2. Yeah, so it's just going to be 1, 2, 3, 4, 5 times 9 times 10 to the 4th is the answer here. So that's 10 to the 4th times 9 times 5. Okay, no digit may be repeated divisible by 5. So, okay, in that case, we know that to check and see if a number is divisible by 5, we just look, the final digit needs to be a 0 or a 5. That's the last digit. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there's one number here, one number here. All right, this is going to be a 0, this is going to be a 5. Now, the first digit can be anything. Oh, okay, no. This can be anything but a 0. And it's a 5 here, so we're good. This is, wait. No, this can't be a 0, but it already couldn't be a 0. So there's 9 options here because there's a 0 here. This is a 5. This leading digit already can't be a 0, so there's 8 options here. Now, that leaves, let's see, no digit can be repeated. We've already taken up 2 digits, so 8 times 7 times 6 times 5. Here, no digit can be repeated. We've already taken up 2 digits, so same idea. So it's, yeah, we've got 9 times 8 times 7 times 6 times 5 plus 8 squared times 7 times 6 times 5. Okay, now no digit repeated, divisible by 4. All right, to check if a number is divisible by 4, you look at the last 2 digits. If the last 2 digits are divisible by 4, then so is the entire number, and that includes 0, 0. But we can't repeat a digit, so we can't use 0, 0. So what we're going to be able to use is, let's see, we've got 0, 4, 0, 8, 1, 2, 1, 6, 2, 0, 2, 4, 2, 8, 3, 2, 3, 6, 4, 0. We don't want to use 44. 48, 52, 56, 60, 64, 68, 72, 76, 80, 84, 86, skip 88, 92, 96. Okay. Now we can separate these into categories to where some of these contain a 0 and some don't. So, okay, if they do contain a 0, if these last 2 digits do contain a 0, then what's the count? Then, okay, we've got these last 2 options are fixed, right? There's only one option here. Now, when we come to the leading term, this can't be a 0. But it doesn't matter anyway because there's already a 0 here. It doesn't even come into play. So this is going to be what kind of does, because we've taken one non-zero number away, just one. So we're left with well, okay, but that means there's 8 options. Right? It's going to be a little bit different for the second case. There's 8 options, right? Now here we've got 7 options, then 6, then 5, because there's been 3 digits have been used. We haven't, and we can't repeat any, right? Okay. So this contains a 0. Now what about the case that doesn't contain a 0? So these 2 slots are filled, but there's a 0 available now, but we can't use a 0 here. So this is 7. Okay, but now once again, 3 digits overall have been used, so 6, 5. Okay. Now, if we multiply these out, this is the case for just, what we can think about is that for all cases where we have a 0 and then another non-zero number, it's going to be the same count, right? So how many cases of when we have a 0 in the last 2 digits do we have here? 1, 2, 3, 4, 5, 6, and that's it. So we multiply that by 6. And then let's see. For not having a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And so there we go. It's going to be 8 times 7 times 6 squared times 5 plus 17 times 7 squared times 6 times 5. Or wait, did I miscount this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And then 1, 2, 3, 4, 5, 6. How many bit strings of length 7 either start with 1 or end with 0, 0, 0? So these bit strings, these strings of ones and zeros. Okay, so anytime we see an OR like this, we think the sum rule, right? Sum all the outcomes associated with the bit strings that start with 1, as well as the bit strings that end with 0, 0, 0. However, any time we see an OR like this, or we're analyzing a problem and we think about how two events are related by an OR statement, or even with an AND statement, you know, for all of the problems we've worked so far, most of the problems, we just kind of quickly analyze the relationships between events and just kind of go with our gut instinct and move forward. And that's because we're working so many problems and we're just trying to learn the concepts here. But really, in reality, and for a real life problem, all of the different events, even within the main problem statement itself, or just the sub events that you come across when working the problem, you're really going to want to analyze all the relationships to see if there's overlap, because it's easy to get caught up in, you know, you see the OR statement and okay, let's go count the number of bit strings that start with 1, get a number, count the number of bit strings that end in 0, 0, 0, get a number, add them up, right? But if you're not careful, then there might be overlap of the outcomes of events, and then you won't get the right count, right? And so like this could apply with an OR statement or an AND statement, right? So we really want to think about, okay, before we just sum or multiply two events, is there any kind of overlap? So, okay, we have bit strings that start with 1. So you could have any 1, 2, 3, 4, 5, 6, 7. They start with 1 and there's anything else. Any combination of ones and zeros. And then there's bit strings that end in 0, 0, 0. And they can start with anything else. Well, yeah, there is overlap here, right? You're going to have some bit strings that start with 1 that also end in 0, 0, 0. So with that, you might say, okay, well, don't we have to draw a Venn diagram now? No, you don't have to draw a Venn diagram, because you could just assume that it's fully overlapping. And then if it's actually not overlapping in certain regions, then you'll mark off like A intersection B, the number of elements as 0 then. So, okay, but we do kind of want to think about how we don't have to draw a Venn diagram, but we want to analyze, okay, what's our entire system here? The entire system is all possible bit strings of length 7, right? So these combinations of ones and zeros, that's the system. And we can actually get that count real quick. So 1, 2, 3, 4, 5, 6, 7. This is permutations with repetition. We're choosing from 2 items, and you can repeat the items. Permutations with repetition is just, it's really simple. So it's the number of elements to choose from to the number of outcome, or the number of slots. So it was 7, 2 to the 7th. That's the number of outcomes in the entire system. Okay, now we want to choose our sets so that we can get what we need as far as subtracting out or whatever we're trying to do. In this case, we don't want to subtract out. In this case, we're trying to isolate what we want. So actually, we're not going to really need this, I don't think. So, okay, what we're looking for is we've got 2 sets within this system here, and we're assuming they're overlapping. Okay, one is all of the 7 character bit strings, 7-bit bit strings that start with 1. So this is set A, and then the other is end in 0, 0, 0. This is set B. So we're trying to get A union B. That's everything here, not including duplicates. So that's what we want, A union B. Okay, so we know that A union B, the number of elements, is going to be the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. All right, so what's the number of elements in A? The number of bits that start with 1. That's going to be 2 to the 6th, right? 2 to the 6th. Because 1 is fixed. It's the number 1. There's only one possible outcome. Then you've got 6 slots. That could be anything. Okay? Now, what about B? How many elements are in B? So how many strings start with or end with 0, 0, 0? Well, it's just going to be 2 to the 4th. Okay. Now, what about A intersection B? How many strings, 7 character strings, both start with 1 and end with 0, 0, 0? Well, okay, it's just, these are fixed at the ends. It's just 2 to the 3rd. All right, and that's it. So 2 to the 6th is 64. 2 to the 4th is 16. 2 to the 3rd is 8. 72. How many binary strings contain exactly 5 zeros and 14 ones, where each 0 must be followed immediately by 2 ones? Okay, so 5 zeros, 14 ones. So, okay, that's 19. So if we need, we could get, the total number of strings, binary strings that are of length 19, and then subtract out if we need. But, or actually, I take it back. We would start by, the system would be, the system would be not all 19 character strings, but all 19 character binary strings with 5 zeros and 14 ones. We could start there. So, yeah, why not? Let's just go ahead and do that. So, that's going to be 19 factorial. Or no, not 19 factorial. It's going to be, yeah, 19, because, okay, we're going to do, it's like you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. You've got all these ones and zeros all over the place, right? But we know that there's 14 ones and 5 zeros. So the rearrangements, it's like if we had all 5 A's and 14 B's, right? You're doing 19 factorial over 14 factorial times 5 factorial. So that's, let's see, going to be 19 times 18 times 17 times 16 times 15 over 5 times 4 times 3 times 2. So 5 times 3 is 15. 4 times 2 is 8. 8 times 2 is 16. So 19 times 18 times 17 times 2. So 19 times 18 times 17 times 2 is the system if we need it. We might not need it. So, okay, now what we're looking for, though, we're trying to get out of the system, is where each 0 must be followed immediately by 2 ones. Okay, well, we can look at this as, so anytime there's a 0 or a 0, 1, 1, let's call that this letter X here, this bold letter X. Well, no, let's do this. Let's call this big B, like for binary. Okay. So what we've got then is, so you've got 5 zeros. So there's going to be, this is 5 times 3 is 15. So there's going to be there's 5 zeros, so there's 5 of these triplets here. So 15 characters are taken up by these triplets. 15 of the 19. So, okay. We've got, let's see, we've got this B, 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 B. Okay. Then we've got mixed in everywhere else. We've got, what are we left with? So 5 times 2 is 10. So that's 10 of the ones are gone. So we've got 4 ones left to work with. And that's it. So is this right? This is 1, 2, 3, 4, 5. That's the 5 zeros, and they're grouped in with the ones, the 2 ones. And then all that's left over is 4 more ones. So what we want to do is, can we just count this, the number of ways to the different words that come out of this? That should be right. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 factorial over 4 factorial times 5 factorial. I feel like that's right. Because there's no other way there's no other arrangement that could happen with this restriction that every 0 is followed by 2 ones. So yeah, that's it. So, okay, we've got 9 times 8 times 7 times 6 over 4 times 3 times 2. 3 times 2 is 6. So 9 times 2 is 18. 18 times 7 is 126. How many permutations are there for these letters here? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and they're all different. A, C, E, G. So 9 factorial. How many start with the letter J and then a vowel? So they start with the letter J and then a vowel. Okay, interesting. So, okay, the consonants are what? You have C, you have G, you have J, M, P, T. And then the vowels, you've got A, E, I. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. All right. So starting with the letter J is easy because now it's just this J is fixed over here, right? So there's no more there's one less constant, and so okay. So we can just ignore the J because it's saying it starts with the J. The J has to start here, and it has to be a J. There's one outcome there. So the question now turns into how many start with a vowel, and not including within this list the letter J. How many words can you make that start with a vowel? That's the question. So okay, this is a little bit tricky because we've got these like a group that's dynamically related to the other group. So we start with the vowel, and now we're left with 1, 2, 3, 4, 5, 6, 7. So, okay, we're picking from 3, right? There's 3 options here. But now the only issue is that the group we picked from and this group we're picking from, they're dynamically related. So we have to be careful. This is where the reorderings can come into play. So, but we do know that once we pick the vowel here, then, so we can't reuse letters, then we're left with, so, okay, this J is not there, but I don't want to erase it at the moment. Well, yeah, why not? I'll add it after. So the J is not there. Okay, but watch, I'm going to forget to put it back for part 3. So the J is not there. And now, so we've used a vowel. So now it's 1, 2, 3, 4, 5, 6, 7. We've got a group of 7 to pick from, right? So it's, okay, 7 times 6 times 5 times 4 times 3 times 2 times 1. right? So, okay, now we're going to be applying the product rule here just because we want to, for each vowel, we want to cycle through all the different, that's a different, for each vowel, you want to go through all those, that's a different word. But the issue here is that we have to think about how, again, this group that we picked from for this is dynamically related to this group that we picked from for this. Again, that's when they can swap places. That's where that comes from. If there's no dynamic relation between the groups, there's no swapping reorderings. Because we could have picked any of the three vowels, right? A, E, or I. So if we write out an example of one of the outcomes, and there's like an I here, well, that I could have been also there's another case where that I was the vowel we picked. So that's where the swapping places comes from. So, but that might not matter because we're counting permutations anyway. So this could be it, because we want to count that, right? That's fine. If one of the examples is you picked an I first, and now you have all of these that you could rearrange, that you picked from we got the number of we could pick from here, right? Well, no, okay, wait, no, that we can't. We have more work to do, because we can't just have this swapping places with just anything, because it can't swap places with a consonant. It can swap places with a vowel, but not a consonant. But that's not going to be an issue because we only picked from the group of vowels. Okay, so we're okay there. We only picked from the vowels. So if it swaps places with a vowel, that's fine, right? If we're listing out the outcomes and we see that there's the I here, but then the I and the E. So yeah, this should be it. So yeah, there we go. So it's 7 times, well, 3 times 3 is 9, so I'll do 9 times 7 times 6 times 5 times 4 times 2. Okay, now, how many consonant, let me put that J back. How many consonant, vowel, consonant, 3-letter words can be made? So we've got this 3-letter word where we're picking from the, so okay, the middle event is easy. It's just 3. Because the group we're picking from the middle is not dynamically related to the outside groups. So we're done with the middle. Great. So now we're just dealing with these two groups on the outside and the consonants. But this still should be simple because it's just permutations. We don't care if they're like reordering. This should just be, let's see, 1, 2, 3. It should just be 6 here and 5 here. Because if we pick a C first, or it's not if we pick a C, it's the different outcomes, right? Let's say there's one outcome where we did C, E, I. Well, without dividing anything out, we're counting the fact that we could have chose C, E, P. We're counting the fact that we could have chose any consonant to start with. We could have chose a P first, and we could have chose a C for this slot, right? So that's where it's like there's another outcome where they swap places. That's fine. We want to count that. We don't need to divide anything out. So that's it. It's 6 times 6 times 5 is 30. 30 times 3 is 90. How many integers can we form with these integers if we want n to exceed 5 million? Okay, so there's 7 digits in 5 million, and we've got 1, 2, 3, 4, 5, 6, 7. Okay. So if the leading digit, we can see if it's a 5, a 6, or a 7, we've accomplished that, because there's no way if we had all zeros remaining, then it wouldn't exceed 5 million, but it's always going to exceed 5 million. So it's the case where the leading digit is 5, the leading digit is 6, or the leading digit is 7. And 5 is we have a little more of a complication because we have 2 5s. So, okay. But we can just sum these outcomes when we're done. I mean, let's think, is there any overlap? No, there's no overlap. You're never going to have if the leading digits are different, then you're not double counting or anything, right? You can't have any integers, 7-digit integers that start with 5 that are also 7-digit integers that start with 6 or 7. So there's no overlap. All right, so we've got, let's see. So we start with a 5. Well, let's actually come down to, let's get a feel for what we're doing here. These will be easier. So we start with a 7, right? So now we're left with 1, 2, 3, 4, 5, 6. So it's just the total number of arrangements of the 4, 4, 5, 5, 6, 7, right? The total number of different arrangements of this, that's going to be 6 factorial over 2 factorial times 2 factorial. So that's 6 times 5 times 4 times 3 times 2. So it's 30 times 6, 180. So there's 180 outcomes here. Now, if 6 is the leading digit, what are we left with? 1, 2, 3, 4, 5, 6. We've got, so 3, 4, 4, 5, 5, 7. So that's 6 factorial over 2 factorial again. So that's 180. Okay. Now, if we lead with a 5, then 1, 2, 3, 4, 5, 6. We've got 5, 6, 7, 3, 4, 4. Okay, so we could just, I guess, just count these. Do we have to think about the 5 switching spots or something? Like divide that out? No, it's just the total number of ways this can rearrange. Or do we? Like, what I'm saying is, are we counting the fact that if these two 5s switch spots? I don't think so. No, because it doesn't, there's no, you put a 5 here. This is like isolated from the rest of the problem. It's all about this here. So, okay, you've got 6 factorial over 5, 6 over 2 factorial. So that's just 6 times 5 times 4 times 3. So that's 30 times 12. 30, 0, 6, 0, 0, 3, 360. So 180 times 2 is 360. And then 360, so 720. Each user in a computer system has a password which is 6 to 8 characters long, where each character is an uppercase letter or a digit. Each password must contain at least 1 digit. How many possible passwords are there? Okay, so we can see that there's this OR criteria here between 6, 7, and 8 character passwords. So we're just going to need to sum the outcomes for each, but we can see there's no overlap. There's no 7 character password that's also a 6 character or 8 character password, etc. Okay, now, so for any counting problem, there's different ways you can solve it. There's different paths you can take. But in this case, the easiest path is going to be, so if this is the entire system, and the entire system is all 6, 7, and 8 character passwords that contain, they contain any uppercase letter or digit, however you want to do it. Okay. Well, then if we think about, we can take out 3 or identify 3 sets that are disjoint within this system. Set A, B, and C. And these sets are, this is 6 character passwords, 7 character passwords, 8 character passwords, but each of these contain no digits. Right? This is 6 character passwords that contain no digits. Same here, same here. So if we just subtract these from the system, then we have what we're looking for, because what's outside of these sets here? If these contain no digits, then everything outside of these sets contain at least 1 digit. And it's all 6, 7, and 8 character passwords that contain at least 1 digit. So that's what we're looking for. And you can still think about this general idea if you had overlapping sets. It's the same principle. It's just, it takes a little more analysis, right? So, okay. The 6 character what we've got is, so we have 6 slots, and each slot could be it's permutations with repetition, right? 1, 2, 3, 4, 5, 6. And you're picking from, there's 10 digits from 0 to 9, and there's 26 letters. So you're picking from 36. But it's permutation with repetition. So it's just 36 to the 6th power. Now, but we want to subtract out. I mean, we could do this at the last step, but or we could do it here. It doesn't matter. Yeah, let's do it. Let's do this. So 7 character. Let's follow the Venn diagram. That'll make it kind of interesting. 7 character, it's 36 to the 7th, right? 8 character, it's 36 to the 8th. So that was everything in the entire system. This was the system, right? And now here we're going to say contains no digits. This is the system. Okay. So now contains no digits, right? Now we're, this is, if we add this up, we've got the entire system, right? But now we want to get the amounts in those sets that we created. So that's going to be, if for a 6-character long password that doesn't contain a digit, that's 26 to the 6th, 26 to the 7th, 26 to the 8th, right? So now all we're doing is we're just taking, the final count is we take the entire system, the amount of outcomes in the entire system, and subtract out those 3 sets. And there we go. That's it. How many positive integers not exceeding 1,000 are divisible by 3, 7, or 11? All right, so we've worked a few problems like this already. You have to understand, to be able to do this, you have to understand the property that these are all relatively prime, meaning they have no common factors. That's going to allow us to solve it. But this is really more about just looking at an application of counting, right? So just trying to look at the steps we're doing here and apply them to a general problem. To solve a problem like this from scratch, it's more for mathematicians. But so the idea is we're using the Venn diagram. That's what this is wanting to illustrate, because we've got so divisible by 3. There's 1,000 integers, but from 1 to 1,000, right? And we want to pick out which ones are divisible by 3, 7, or 11 and count the total outcomes. The problem is these outcomes could be overlapping. There could be some integers that are divisible by both 3 and 7, but maybe not 11, or divisible by 7 and 11, not 3, or divisible by 3 and 11, not 7, or they're all 3 are divisible by the same number. So, we don't have to draw the Venn diagram. I want to stress that. You could just assume that all of your sets are fully overlapping, the sets you're trying to pick out, right? The system would be, let's just show you the analysis here. The system would be all integers from 1 to 1,000, right? That's the system. And the set we're trying to get out of here is, and we'll just assume they're overlapping, even if they happen to not be, or only overlapping to some degree. We're going to assume that that this is A, this is B, this is C, and we're assuming that they're overlapping again, even if they're not. Just you can do that. But the idea is we're trying to pick out here. We want to get A union B union C, where A is all of the integers between 1 and 1,000 that are divisible by 3. B is all the integers between 1 and 1,000 divisible by 7. C 11. And A union B union C would be all of those together with no duplicates. That's the big key. We don't want duplicates. So, okay, we can write this out. A union B union C, the number of elements, you've got the number of elements in A plus the number of elements in B plus the number of elements in C, then minus, and this is going to be these pairs. There should be 6 of them, I think. 3 choose 2, 3 factorial over 2 factorial. Or no, there's 3. Yeah, 3. So this is A intersection B minus A intersection C minus B intersection C, and then plus A intersection B intersection C. Okay, so the number of elements in A is how many numbers or integers from 1 to 1,000 are divisible by 3. What we do is we do the floor function of 1,000 divided by 3. Because it's the floor function because... So this should be 333. And it's the floor function because, okay, if we're counting, right, 1... or no, we start at 3, 6, 9, 12. So if we add, if we do 333 times 3, we get 999. So that means we added 333 times, but we can't go the 334th time. So yeah, so this is 333, and then the B, number of elements in B is 1,000 divided by 7 floor function, and then 1,000 divided by 11 floor function is going to be the number of elements in C. So and then divided by 11. So 142 and 90. Okay. 142 and 90. 142, 90. Now these intersections is just where the whole relatively prime comes in. We can just say that the numbers between from 1 to 1,000 that are divisible by both 3 and 7 are just, we take the floor function of 1,000 divided by 3 times 7. If they weren't relatively prime, meaning if they had the, like even 8 and 15 are relatively prime because they don't have the same, any of the same factors. So that means you could do this between these two. This you could check for what we're checking for this way, between those two. All right, so 1,000 divided by 21 is divided by 21, 47. Okay. 1,000 divided by, let's do, A intersection C, so 3 times 11. So divided by 33 is 30. So minus 47 minus 30 minus, and then 1,000 divided by 7 times 11 is and then so 12. Okay. Now the A intersection B intersection C is going to be the floor function of 1,000 divided by 3 times 7 times 11. So 1,000 divided by 3 times 7 times 11. 4. Okay. And that's it. That's, we're looking for A union B union C. We're not trying to subtract it out. So, all right, 333 plus 142 plus 90 minus 47 minus 30 minus 12 plus 4. 480. Three types of bread, 5 types of meat, 3 types of cheese. How many different ways to make a 1 meat, 1 cheese sandwich? Okay, so we've got the first event, we can choose from 3 types of bread. Okay, but now the second event is completely independent from the first event. There's no overlapping. We're not pulling from the same set. So this is not a permutation or anything. We've got, okay, we can choose 1 of the meats and then 1 of the cheeses. Just apply the product rule, right? So you pick white bread, cycle through the different meats and cheeses. Then you pick, wheat bread, cycle through the different meats and cheeses. But remember, there's no reordering here. That's not, okay, we picked white bread here, bologna here, and Swiss cheese here. Well, we have to divide out if we switch the W and the S. No, that doesn't make any sense here. These are independent. We're pulling from independent groups. You can't have a cheese over here. So the answer to the first question is 15 times 3 is 45. Okay, the second part, it's the exact same idea. We've got this event 1, event 2, and event 3 associated with the breads, the meats, and the cheeses. But now it's just, okay, we can still just choose 1 bread, so it's 3 here. But then now we can choose, well, it's 1 meat again. But here we can choose, it's 3 meats. Okay, so we could, all right, let's see. Well, if it depends on what they're saying. If they're saying like we have to choose 3 meats, then in that case, the order doesn't matter of how you put the meats, right? So we're just going to say, what's the total amount? What's the total number of outcomes here? This is like its own separate counting problem. We could go to a separate page of our notebook and say, how many different ways can you choose 3 meats from 5 where order doesn't matter, right? We're just trying to get a count. Well, how many different ways can you choose 3 meats from 5 with order doesn't matter? It's 3 choose 5. Or no, 5 choose 3. Right? And that's the number of outcomes here. And that's what we're going to put in this slot in the middle for the meats. We're applying the product rule between the breads. Instead of just 1 outcome for the meats, there's 5 choose 3. And now with the cheeses, there's 3 choose 2. So if we're required to choose 3 meats and we're required to choose 2 cheeses, this is the answer. So this is potentially 1 answer. 3 times 5 choose 3 times 3 choose 2. But there's another potential answer if they're suggesting that we could choose 1 meat if we wanted to and 1 cheese, or we could choose, like anything, like any combination we want. In that case, so, okay, this is one part where we chose 3 meats and 2 cheeses, but then we have to do, okay, we could choose 2 meats, 2 cheeses. We could do 1 meat, 2 cheeses. We could do 2 meats, 1 cheese. We could do 3 meats, 1 cheese. Like, you have to go through all the different combinations and just do a separate counting problem and then add them all up. Now, but you just want to be careful and think about, are there any overlapping outcomes with these OR criteria? But there shouldn't be. There's no way you can have a 2 meat, 2 cheese sandwich and at the same time have a 1 meat, 2 cheese sandwich, right? So there's no overlapping outcomes. So these are just these pure separate counting problems that you just need to add up. There are only computer science and math majors in discrete math. There are 53 computer science majors, 28 math majors, and 17 who are double majors in math and computer science. How many people are enrolled in discrete math? Okay, so the total system is everyone that's enrolled in discrete math, and they're saying there's only computer science in just pure mathematics majors in the discrete math class. So computer science math majors. So there are 53 computer science majors. They are definitely majoring in computer science. There's 28 who are definitely majoring in math, and there's 17 who are double majors. So how many people are enrolled in discrete math? So we're looking for this. Or no, I'm sorry. We're looking for, well, no, okay, yeah. I didn't draw this right. We're looking for this, C union M. And this is out here is 0. It's kind of confusing because every single person that's enrolled in the class is computer science or math major. So we want C union M. So C union M, the number of elements, is everything in C plus everything in M minus intersection of C and M. So everything in C is 53. Everything in M is 28. C intersection M is 17. So 53 plus 28 minus 17. There we go, 64.